So moving on, we'll talk about the data plane now. Since the control plane is securely brought up, what we want to do and what the whole SD-WAN solution is to securely connect edges. What do we mean by securely connect? We want to connect it. What we use is IPsec tunnels. We could also use GRE, but essentially what we use in our data plane is IPsec to connect all the edges to each other. So essentially, the SD-WAN architecture in Cisco is going to bring your data plane in a full mesh topology using IPsec tunnels. What the data plane is essentially the routed traffic that we spoke about right up front. The control plane was the routing traffic, the exchange, forming a secure channel between the edge and the controllers to exchange the routing packets. Now we need a secure channel between the edge devices to get the routed traffic overhauled from one end to the other end. So bringing up the network for routed traffic.
So when we're talking about the different encapsulations or methods by which we're carrying this traffic, we're talking about IPsec and GRE that's being used here. These are standards-based protocol, and we'll delve deeper into how we construct them in this environment. But for the purposes of what we're using to carry the traffic, we're using standards-based technology.
Thanks, Ali. So essentially why we need a secure channel is because this routed traffic is running over an unsecure internet. If you have an MPLS line or a private network, you essentially could get past the security aspect of it, but now your data is going on an unsecure channel. What you need is some security protocol that actually forms a secure channel for your branch devices. What does IPsec need? It requires a key exchange. Why it requires? So let's talk a little bit about security over here. I won't delve too much into details, and Ali can keep me honest. So what we have is, if you have data D, we could have two sets of keys, let's say P and P prime. You could use key P to create a jumbled version of D, which we can call D of P. And the only way to get D back is to use P prime. Okay.
So this is where we're describing asymmetric encryption.
Asymmetric keys, yeah. So we'll talk about symmetric key exchange at some other point, but essentially what I want to highlight is we need a set of keys in order to secure a channel. If you hold on to one key or at your end, that's your private key, and provide this public key to everyone else, I can jumble my data using my private key, which resides only at my end, jumble the data, run it over an unsecure channel, basically get it to the far end. The far end could then use my public key to actually decrypt the data, to actually get to know what was contained in the packet itself. As long as I keep the private key secure, nobody should be able to pretend to be me or be able to get to decrypt this data itself.
So fundamentally, we're talking about that to ensure security for our data, we need to leverage keys.
Yes.
And those keys can be used in a number of ways to secure our data, but fundamental to building this infrastructure is that we need to know that a key exchange needs to happen.
Exactly. So basically, a public key is what you would use. So if I want to, let's say I want to communicate with you, Ali, what I would do is you'd give me a your well-known public key. I would use that to jumble the data I want you to read. You hold on to your private key, which nobody has, and you're the only one who can actually decrypt what I'm saying, and hence you will be able to interpret what I have sent to you, and none of the other people, even if there's a man in the middle, should not be able to decrypt the data I'm sending because you're holding on to your key. What we want to do in terms of a key exchange is provide this public key essentially to all the other edges so that I can start communicating with each of the edges. I need everyone's public key in order to start communicating with them. So what's the component that can help me exchange these keys? There's one component that's common to everyone. Everyone connects to the controllers, the vSmarts. So the vSmarts not only contain the routing information base like we discussed before, now also act as key exchange servers. So everyone reflects their keys from one end to the other to let everyone know how to actually get data from one edge device to the other edge device over the unsecure internet. So the vSmart is a key exchange server as well. So that's how, so the data plane bring up essentially consists of this. You get your control plane up, you exchange your keys, you exchange routes, and by routes, the first set of routes that you exchange is the actual location of the device itself. You let each edge device know that, hey, if you want to talk to this data center, you need to get to this IP. Conversely, you let the data center know, hey, if you want to talk to this campus office, you need to get to this IP. A bidirectional tunnel is set up using IPsec. And how is the tunnel set up? Basically, you have exchanged your public keys over the key exchange server, which is also the vSmart. And now you have a channel between these two, which will essentially let you talk in privacy to the two different endpoints. And since this is a full mesh topology, every edge device knows about all other edge devices via the controllers itself. What additional advantage you get is, since you have a common set of key exchange servers, you can rekey at will, you can rekey as often as you want, you can get this secure channel up and running and keep generating a set of symmetric keys as often as you want in the network to make sure that your hash is as secure as you can get it. Like, you essentially can't crack this key using a log table and large compute. Messages would switch over to a different key pretty frequently.
So our architecture gives us the ability to have very efficient key exchange and ensure that we have the strongest cryptographic methods for our data.
Yes, exactly. So because we have these controllers which are performing that key exchange for you, you don't physically have to sit on each box to figure out, okay, I need to program new keys, I need to program these keys to the remaining 5,999 sites. This all happens automatically without intervention from any network operator. The key exchange is taken care of and the network is secured at all times.
To clarify one point, between the control plane, we use asymmetric encryption, but between the data plane, we use symmetric encryption.
Yes, yes. So I won't be, yeah, but that's exactly what we use. but I'm not delving deeper into that. We shall do that in some other section. So now that you have your data plane up, you essentially can communicate between any of the edge devices. Each of the edge devices can further be segmented into VPNs, and in Cisco terminology, it's a equivalent of a VRF. So each VPN on an edge can talk only to a VPN, the same VPN on the other far end edge. So it just...
So when we use the term VPN or VRF, which are standard terms,
Yes.
what we fundamentally mean is a logically separated layer 3 domain.
Yes, exactly. So what it further means, if you want to really dig deep, is each VPN is its own routing information base, its own fib. Okay, so you can split a router into multiple routers by using VRFs or VPNs. That's exactly what this is. So when I say an edge device, a V edge or a C edge, it's essentially into the number of VPNs. It's that many routers. So if I have 10 VPNs, I have 10 routers in one box residing at each edge. And each of these VPNs has its own routing information base, own forwarding table. No information is leaked between these VPNs. Hence you get segmentation and security over there at the edge itself. The secure channel over the data plane is through IPsec. So all the VPN traffic on one box can be aggregated, pushed onto this secure IPsec channel, pushed down onto the far end device. The far end device then again splits this up based on these different VPNs, refers to its routing table for that VPN, and then forwards the traffic down. So you have 3 levels of segmentation. You've segmented controllers, the edges, you've segmented the edges itself, and within the edges you have segmented it through VPNs or VRFs.
So Vinay, I have a question. You mentioned early on that internet is one of the legitimate types of transport. And one thing that happens on internet is IP address changes. Now you also mentioned the data plane connectivity between the edge devices themselves. So what does happen to the data plane connectivity when the IP address actually changes?
So if the IP address actually changes, there will be a data plane interruption because the IP address has changed, but that'll be just temporary. The automated bring up that we just discussed, all the steps going back to the VPN, the controller, getting the new IP address translation is all automatic, and the data plane will be restored within a few seconds back again with the new IP address.
So it's fully automated
it's
from
fully
both
automated.
control and data plane.
Yes, you really don't need to know about the IP address change or manage it per se.
And obviously, if you have other types of transport, then only one of them gets interrupted.
Yes.
You still have the other ones to take over the load.
Yes, so you generally have redundancy at the hardware level. You'll have redundancy at the network level itself, the transport level, and you'll have redundancy on the controller itself based on where they are located. So physical, geological, and the underlying software itself, you'll have redundancy over there. So that's basically what the SD-WAN architecture is all about. There is another aspect, the key exchange servers are also secure. You may say that, hey, these guys may reside in the internet. Is that secure? Yeah, it's not. It doesn't need to reside in the internet. You could have these all in a private network. All you need is the orchestrator in the public network. The orchestrator doesn't have any keys, has no information, no routing information about your network. The rest of the controllers can reside in the private network, which can be secured, and you'll still be able to bring this whole overlay up. So our whole architecture is a secure, extensible network based on the SD-WAN solution for the internet. So any more questions you guys have?
No, I think we're good.
Okay.
Thanks, Vinay. So we've covered quite a bit with the SD-WAN architecture here. We looked at the evolution from the past to the future, where before you had a single box carrying all of your control plane and I/O functions, to the new model where things are abstracted. When we look at the SD-WAN architecture as was described, we've seen the abstraction of CPU components being abstracted into what are called vSmart or control plane elements. We've seen the abstraction of the I/O component to become the edge router. And we've seen that the backplane that was on the physical router has become the actual transport fabric between these control elements and edge elements. The overall SD-WAN architecture is a fully cloud-delivered, fully automated system made up of a number of components that establish control plane relationships to establish secure data plane relationships to carry network traffic. Thank you everyone for joining us for this session, and we hope to see you in the next sessions.